Welcome back to our video series on PCB layout-driven design with VSS. In this video, we're going to take a look at interconnect design, and we're going to do it in two steps. In the first step, we're going to add the interconnects. What we're going to do here is for the explicit RF signal path, in other words, the path that we know is carrying RF signal, we're going to use M-trace and MC-trace elements to not only model that signal path, but also to help us lay it out. Where necessary, or where we think there's high degrees of coupling because of the way component pinouts are arranged, we're going to add coupled line models. And we'll use some INETs where we want to sort of be lazy. INETs are very easy to route, and they allow us to wait to take into account the electrical effects of those lines. And we'll do that by using ACE in this video, and in a later video we'll use Axiom to verify the whole thing. And then in step 4, we'll actually do the ACE analysis. This gives us a very fast, somewhat accurate analysis. ACE is not an EM solver, but it does incorporate models which run EM on much smaller parts of the design, only where it's necessary. And this allows us to very quickly tune and optimize the lines to improve performance because we don't have to wait a very long time for complex EM analysis to run. But one of the really great things about the AWR design environment is that we can do this ACE simulation while running a VSS system-level analysis to see the impact of the interconnects on EVM. So let's get back to our design. If you remember, this is what our VSS level design looks like, and I'm going to zoom in on exactly where our interconnects will come from. Again, the same element I've been using before in this VSS simulation chain is a nonlinear simulation-based model, but this time I'm pointing to a microwave office design called RF signal path board. And what RF signal path board is basically my entire transceiver design, or at least my design from the transceiver chip all the way to the antenna. And what we want to focus our attention on here is the RF signal path. The transmit side is a little bit more interesting than the receive side because of the nonlinearities of the power amplifier, and that's what we've been focusing on in the previous videos. So let's follow the signal path at least up to the power amplifier. Well, coming off the transceiver chip over here, you can see that I have a 6-coupled line structure. And the reason why I've chosen to do that is because I know from the pin assignments on that chip that I have my transmit and receive side signals very close to each other. So I want to analyze that potential coupling there in case I have a feedback path someplace further down on my chip that may cause an oscillation. Continuing further on our signal path, you can see that once I come off of the coupled line structure, I have 2 parallel MC traces, then I have 2 blocking caps, and then 2 more parallel MC traces. Now the reason why I decided to use the this is the M trace over here, not the MC trace. The reason why I decided to use the M trace instead of tiling together lines and bends is because I want the freedom to be able to route these structures, and the M trace gives me that freedom because it's a fully routable line. And what I'm obviously not going to be able to do immediately is capture the coupling between those lines, but I'm going to allow ACE to do that for me. So what do I mean by that? Well, if I go and look at the layout for this board, we can see over here that coming off the coupled line structure, I have my parallel lines, but then they aren't parallel anymore because I needed to make room to put in my blocking caps. And then I have 2 more lines that are somewhat parallel over here, but then they diverge to go into the balun. Now the reason why, again, that I wanted to use the M-trace lines is because I have the freedom to route each line individually. There will be some coupling between those lines for the parallel segments, but not for all the lines, so it'd be much more difficult to tile together a schematic that takes into account all the relationships between the parallel lines. So again, I'm going to let ACE do that for me later on in the signal flow, or later on in the analysis. Well, how do I do that with ACE? If you're familiar at all with the extract capability, let's go over here. Let's zoom out one more time. And over here, you can see I have two extract blocks set up. One is for ACE and the other is for Axiom. We're going to use the ACE one here in a minute after we take a look at the iNets. But this is what's going to allow us to switch from just modeling the interconnects with the elements that are on the schematic, the microstrip coupled line structure and the M-trace elements that I showed you already, and include any other lines as well as finding couplings among those elements that I've already added. Well, where are some of those other elements? We've already looked at some of those couplings in the M-trace elements, but where are some of those other lines that I'm talking about? Well, here on the control line for my power amplifier, you see an NCON element, a named connector element, and that's going to attach back to a similar element with the same name on the transceiver chip, and that gets implemented in the layout as iNet routed lines. And you can see, as we zoom in, you can see where those routed lines are. They're deep within the board, right here, and they come over to our PA chip. I have two of them, and they're coming off of control lines on our transceiver chip. Now, these are simulated right now as shorts until I go into the extract block and change its state from disabled to enabled. So let's go ahead and do that. We'll change its state right there. Okay, and now it's turned on. Now instead of ignoring those iNets and ignoring the couplings between the M-trace, ACE is going to find those for us. Well, how does ACE do that? Well, the first step that goes on in the extract block is that it pulls out all the artwork and inserts pins so that we can connect things back up again. So here you can clearly see our microstrip coupled line structure over here, some of those M-trace lines over here, and you can see our iNets included over here. Now this is a multi-layer board, so some of these things have ground planes in between them, and so they may not couple at all layers, but they may couple at some of them, and that's what we want to be able to capture and see. ACE actually produces a net list of what components it's using to model these lines, but we can go in and see a very graphical analysis right here, and let me just re-simulate it. So you can see the multiple three-dimension structures. These resistors over here are modeling our vias. If we look at a very high level, you can see coupled line structures are discovered. If we zoom out a bit, you can see our 6 coupled line element that ACE also was able to find. And if you look over here, here's that coupled line element that we knew would exist, but we modeled as M-traces. So in the original simulation for this RF signal path board, we won't have that coupling. We'll just have the distributed effect of the individual microstrip lines that I'm showing here. But in the ACE-based simulation, we will get the coupled line structure involved, or having an impact on our design, assuming that there is an impact. Well, what is that impact? We do care at the microwave level what's going on, and we can look at things like P1 dB, gain, power out, all the things that a RF microwave circuit designer would be interested in, but we've been focusing on what the system level performance of this board is and how we can look at that while we're doing this interconnect design. Well, I've run the EVM analysis previously, and let's run it again here. And we'll see what the effect is with and without the board, the signal path on the board. So that's our VSS EVM simulation with the ACE analysis incorporated. And if you remember back to our original simulations with just the packaged power amplifier, this is essentially the same performance. It's somewhat degraded, but not much. I think we're losing maybe 0.2% of EVM at 24 dBm out. But we've essentially been able to recapture all the performance that we lost with the ideal board that we showed in the last video. And this is including directly that ACE analysis. If we want to tweak the interconnects a little bit and move them around, we are free to do that. We can go move some lines and rerun the analysis, and it doesn't take very long at all, as you saw. And we can see the impact directly on EVM by doing that. So if you'd like more information about anything I've shown you, how to use those microstrip coupled lines, how to use the M-trace model, how to use iNets, what ACE is all about and what's involved in setting ACE up, or how to incorporate all that wonderful interconnect analysis, the richness of what Microwave Office has to offer into a VSS system simulation. There's plenty of information on the AWR website. You can download a demo copy of Microwave Office and VSS. And if you still have more questions, I encourage you to contact your AWR sales professional.